to help explain two-way between groups, between subjects, ANOVAs, what I'm going to do is first remind you how a one-way ANOVA worked, and then I'm going to juxtapose that with the two-way version. And so you can see how the math works for both of them. So what I've got here is a situation where we're doing a study where we're measuring alertness again. We have three groups in this case. We have people who drank decaffeinated Mountain Dew or coffee, some decaffeinated condition, people who drank Mountain Dew, and people who drank coffee. And so these are the raw data in here. So there's 6 people who drank decaffeinated coffee, 6 people who drank Mountain Dew, and 6 people who drank coffee. Right, so these are the actual raw data that we're going to analyze. I've already put this data through a statistical software program, and it gave me this source table. Right, so here's the sums of squares between, the degrees of freedom between, the variance between, the within groups, sums of squares within groups, degrees of freedom, the variance estimate from within the groups. This divided by this is 1.66, and there's the p-value. So now we can already tell, in this case, that for this data, there was not a significant difference between the 3 different groups. We were unable to reject the null hypothesis, which in this case would be the mean of the decaf is the same as the mean of Mountain Dew, which is the same as the mean for coffee. So for this data, we cannot reject the null hypothesis. And we can draw the bar graph, right? So this isn't a histogram. This is going to be bars that show the mean. So overall, the decaf folks, the mean of all 6 of these people, you add up these scores and divide by 6, and their mean is 7. For the Mountain Dew folks, I did it earlier and I got 8. Here, this is 7.00, 8.83, and for coffee it was 9.83. 9.83. So the mean of the 6 people in the decaf condition is 7. So there's 6 people in here, and that's their average alertness score. Right, the mean of alertness. For the 6 people in the Mountain Dew condition, their average alertness was 8.83, and for the coffee, it's 9.83. So it looks like overall coffee increased alertness, but it's not a big enough difference for us to reject the null hypothesis that these all came from the same population, and they vary just due to random sampling. So the first thing I want to do is connect this raw data to the variance estimates, which is something that we've already talked about doing for a one-way ANOVA. So this is a review, but really I've set it up a little bit differently here, so it's kind of nice to think through it again, right? So we're going to calculate the within groups variance. This is this mean square within. This is our variance estimate within. And remember the way that we calculated this is we have 3 groups here. So we have our variance estimate from our decaf, plus our variance estimate from Mountain Dew, plus our variance estimate from coffee. And we're just going to add them all up and divide by how many there are. We're just taking literally the average of these. And you can only do that when the sample sizes are the same across the 3 different conditions, but I've set it up that way to keep things simple. And so to remind you just how this works, first I'm going to calculate the variance estimate for the decaf group, for these folks, right? Where does this come from here? So the formula for this, right, it's the variance, so it's the sum of squares divided by the degrees of freedom for that group. Right, so it's the same variance formula that we've talked about since the start of this class. Notice I've just put the mean of the decaf condition here, and we're going to have the degrees of freedom from the decaf because we're just calculating the variance of these 6 people. And the mean for the decaf, right, I already told you that, is 7. Alrighty, so we'll calculate the variance for the decaffeinated conditions. We got 4 minus 7 squared plus 5 minus 7 squared plus 6 minus 7 squared plus 8 minus 7 squared plus 9 minus 7 squared plus 10 minus 7 squared. And that's divided by the degrees of freedom for this group, so that's the sample size for that group, minus 1. Okay, s squared. So we're calculating the variance of these 6 scores. So that's one of our within groups variance estimates. We'll have the 3 that will average. So here we got negative 3 squared plus negative 2 squared plus negative 1 squared plus 1 squared plus 2 squared plus 3 squared divided by n. 1, 2, 3, 4, 5, 6. There's 6 scores in there. 6 minus 1. All right, we got 9 plus 4 plus 1 plus 1 plus 4 plus 9 divided by 5. So that's going to be 10, 20, 28 divided by 5. And that is 5.6 equals the variance of the 6 people in the decaf condition. So these folks are 5.6. So maybe I'll say 5.6. And we could go through and do the same thing for these 6 folks and these 6 folks, but I've already done that. And when I did my calculations earlier, I got 8.57 for the Mountain Dew group for their variance and 8.17 for the coffee group. All right, so we can calculate this now. So we got 5.6 plus 8.57 plus 8.17 divided by the number of groups, which is 3. And I got 22.35 divided by 3, which is 7.45. So our mean square within groups, the average of our 3 within groups variances, is 7.45. So that goes right here. And the only reason these differ is rounding error. Right, so this, with equal sample sizes, this is calculated just by calculating the variance of this group, the variance of this group, the variance of this group, and averaging them. So that's a within group variance. Notice, once we've got this within group variance determined, we can calculate these afterwards. So the degrees of freedom within, recall, is the degrees of freedom for each of the groups added together. So that's the degrees of freedom decaf plus degrees of freedom Mountain Dew plus degrees of freedom coffee. Right? And for each of these, it's the number in that group minus 1. So there's 6 people in this group, 6 minus 1. 6 people in this group, 6 minus 1, plus the number of people in this group minus 1. So that's going to be 5 plus 5 plus 5 degrees of freedom within. It's going to be 15, which is right here. And once you have these two, recall that the mean square within is the sums of squares divided by the degrees of freedom. So we know the mean square within, that's this. We know the degrees of freedom, that's this. So we could just calculate. We can plug those in and calculate for the sums of squares in that case. So 7.44 equals an unknown sums of squares divided by 15. So in this case, you just multiply both sides by 15. These would cancel out, and the product of these is going to be about this. It might differ a little bit from rounding error, but you can calculate this that way. Of course, you could have started from the raw data and calculated the sums of squares directly, like I showed in that previous video. So that's a way it could have been done as well. And that's what you would have had to have done if you had unequal sample sizes. Okay, well, we've calculated the mean square within, but for our f, we still need our mean square between. And remember, conceptually, what this is we use the, we go from our observed sampling distribution, our 3 sample means, and we go up to estimate the population variance that way. And to do that, we take the standard error squared multiplied by the sample size. In this case, that'll be 6. Right, so first thing we need for that is to calculate the standard error squared. That's the variance of the sampling distribution. So we're going to use a variance formula. Right, here's the regular old variance formula that we've used the whole class. But now we're doing it on our 3 sample means. So those are actually going to be our data points. So I'll put those in here. So these are 7.00, 8.83 is the mean there, and 9.83 is there. And so these are means. Notice they're on the margin of this table. So these are called marginal means here. If we calculated the mean of this group, which would be 7, we did that earlier, right? That's a cell mean. Cell mean, cell mean, cell mean, marginal mean, marginal mean, marginal mean. Okay. All right, so we got our 3 data points now. We'll calculate their variance. So 7, we need to have the overall grand mean, the mean of all of them, and that I calculated earlier as 8.55. So we have 7 minus 8.55. So this 8.55, that's the average of all 18 people in the whole study. And because we have equal sample sizes, it's also the average of these 3 sample means. All right, so we need the first score minus the mean of that distribution squared plus the next score, 8.83, minus the mean of these 3 scores, the mean of that distribution. And our third and final score, in this case they are sample means minus the mean of the 3 scores that went into it. And then this is going to be divided by the degrees of freedom for these means. That'll be 1, 2, 3. It'll be 3 minus 1 eventually. SE squared. Right, so this is negative 1.55 squared plus 0.28 squared plus 1.28 squared divided by the number of scores, 1, 2, 3, minus 1. 1.55 squared is 2.40 plus this squared is 0.078 plus this squared is 1.64 divided by 3 minus 1 is 2. Add all these up, 4.118 divided by 2, that is 2.059, and that is the variance of these 3 scores. It's the variance of the sampling distribution. So now we got to go from the sampling distribution back up to the population. And that's just this number that we just calculated times our sample size. Remember, when you go down, you always use the same sample size to create your sampling distribution from your population distribution. So we're going to keep our same sample size going up, and so that is 6. It's 6 in each of these cases. So our mean square between, which is our estimate of the population variance based on our 3 sample means, is the variance of the sample means 2.059 times the number of people in each of those groups, 6. So that's going to be 12.35. So that goes right there. And again, it's a little bit different at the very bottom, and that's just due to rounding errors. So they're really the same number. So now we've gone from our raw data, and we've calculated our variance estimate between groups and our variance estimate within groups. And with this number, it'd be pretty easy to determine the sums of squares between and the degrees of freedom between. The degrees of freedom between is just the number of groups. The number of group means minus 1, so that's where this 2 came from. 1, 2, 3, minus 1 is 2. And we could get this really easily. So the mean square between is the sums of squares between divided by the degrees of freedom between. All right, so we can just multiply it by degrees of freedom between. So to get this 24.78, what you do is you multiply the mean squared by 2. So this times this is this, just like this times this is this. With our variance estimate between groups calculated and our variance estimate within groups calculated, we can calculate our F statistic. Well, that's just the variance estimate between divided by the variance estimate within. So in this case, that's 12.39 divided by 7.44, and that's how you get 1.66. And this isn't very far from 1, and remember, if the null hypothesis is true, the most common F statistic is 1, and this isn't very far from 1, which means that our sample means didn't differ very much compared to what you'd expect if the null hypothesis is true. And so here, right, our p-value is greater than alpha, so we fail to reject the null hypothesis. All right, so now what I'm going to do is I'm going to use this exact same data, but we're going to switch it to a two-way between subjects ANOVA, and then you can see how the process is very similar, and also how it differs a little bit with the interaction. So now what I want to do, since we just reviewed how a one-way ANOVA works, I want to compare that with how a two-way ANOVA works. So this here is the exact same stuff I just talked through. And what I've done here is I've got the two-way between subjects ANOVA. So first off, I want to point out that I've just taken the data, the raw data, and copied and pasted it over here. Right? So this is 4, 5, 6, 4, 5, 6, 8, 9, 10, 8, 9, 10. But now what's going on is all of these 9 people, these are actually going to be guys. And these 9 people on the bottom, these are going to be girls, right? So it's a two-way ANOVA because we have drink across the top, and over here we have gender. So we have 2 independent variables now, drink and gender. It's between subjects because each person's in only one of these cells. So this 4 is a single guy in the decaf condition, and of everybody he had the lowest alertness score. This 14 is a girl who drank coffee, and of everybody she had the highest alertness score. Right, so it's a two-way between subjects ANOVA. I put all this raw data into statistical analysis program, and it gave me the source table right here. So there's some stuff I want to point out. So first off, the sums of squares total, remember those are just the sums of squares ignoring all groupings. So that means the sums of squares total should be the same for both because the data is the same. Right? And the degrees of freedom total also ignores grouping, and so those are the same. And recall that the degrees of freedom total, that's just the total number of participants ignoring grouping minus 1. So in this case there's 18 participants minus 1, so that's where the 17 came from. So the next thing I want to do is compare our results for drink, the effect for drink over here, with it over here. So recall before, when we looked at this, we decided that we couldn't reject the null hypothesis that there's no effect of drink, right? So really, this right here, this row, is the drink variable, right? Here we've just directly labeled it drink because drink is between, gender is between, and the interaction is between, right? So they're all between now. So now we would say that this is the main effect of drink, this is the main effect of gender, and this is the interaction between drink and gender, right? This will tell us if the effect of the different kinds of drink on alertness differs for men and women. And so we're going to focus on the main effect of drink right now because that's one we did before. So remember, to calculate the mean square, what we did is we took the 3 sample means, we calculated their variance, and we multiplied it by the sample size. And that's how we got 12.39. So to do the main effect of drink over here, and to get this mean square, we're going to do the exact same thing, right? So when we're calculating the main effect of drink, we ignore gender. right? So we're still going to have a mean of 7. This marginal mean for decaf is going to be 7. This will be 8.83, and this will be 9.83, just like it was before. And we calculate their variance and multiply it by the 6 people that went into each of those. We're going to get the exact same 12.39. So that's why these are identical. You're ignoring gender altogether when you're calculating this. But now, if you see the F statistics, they're really different. And they're different because the F statistic is the mean square between divided by the mean square within. Right, so for these F statistics, the top is both 12.36, and the bottom is the mean square within. So here it was 7.44. Now the mean square within is 1.83. So the mean square within is dramatically smaller. Right, so how did that happen? So recall, this 7.44 is just a straight up average of the variance of these 6 numbers, these 6, and these 6. So we calculated the variance here, the variance here, the variance here, added them up, divided by 3. We just took their average, and that was 7.44. Well, this is produced by a similar process, but now you do it with the 6 groups. So you calculate the variance here, 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 here. You add up those 6 variances, and you divide it by 6. Remember, you can only do that with equal sample sizes, but that's what we're working with here. There's 3 people in each group. So you can think of this as there being 6 estimates of the population variance, 1 for each cell, and we're just averaging those 6 variance estimates. And this is so much smaller than this because the scores varied a lot here. They went from 4 to 10, right? 5 to 12, 6 to 14 in those cells. But I set it up such that guys were all similar to each other, and girls were similar to each other, but guys and girls were very different, right? So this only goes from 4 to 5 and 8 to 10. So there's a lot less variability within each of these cells than there was here. And that's reflected in these much smaller averages of those variances, right? So what that means is when we calculated this F, right, we got a pretty bad looking F. We weren't able to reject the null hypothesis like we were hoping to. But here, because we've separated guys and girls, our mean square within it is very small. And it ends up having a 12.39 divided by 1.83 is 6.76. which has a p-value of 0.01. So this is less than alpha of 0.05. Now we can reject the null hypothesis. This is the exact same data. Before, drink was not significant. Now it is. It's significant because controlling for the variation across gender, our mean squares within was smaller, resulting in a bigger F, and we can reject our null hypothesis. So that's great news. And in practice, sometimes you have data like this, and there could be a variable like gender that could reduce your mean square within, your variance estimate within. And if you know what that is, you could just collect that variable and include it in your analysis, and you'll have more statistical power to detect effects that are really there. And gender is actually a common one because men and women often differ on whatever we measure. They often don't differ a lot, but they do differ a bit. And so getting rid of their extra variation, grouping it better, you could say, and getting a smaller denominator for your F will increase your statistical power. Next, let's talk about the main effect of gender. So what that's referring to up here is ignoring drink. Do guys and girls differ? So what we need to do for that is calculate the overall mean for guys, which I calculated earlier as 6.33. So you just add up these 9 numbers and divide by 9. And for girls, you just add up these 9 numbers, divide by 9, and you get 10.78. All right, so are these two significantly different from each other? Right, we're ignoring drink altogether when we're looking at gender. So to calculate the mean square, we just calculate the variance of these two numbers just with a regular old variance formula. We multiply it by 9 because there's 9 people that went into each of these means, and you get 48.49 when you do that. So it's the exact same process except for you just use it as it was with drink, but now we're just doing it with these two means, these two marginal means here. So that's how we got this mean square of 88.89 for gender, right? And then the degrees of freedom, of course, you could figure out because there's 2 groups, and degrees of freedom would be n minus 1, so 2 groups minus 1 is where this 1 came from. And if we wanted to figure out how to calculate this gender, you multiply this times this, and that gives you the sums of squares. So it's already pretty obvious that that works out that way. So our F statistic is going to be just like it was before, mean square between. So this is our mean square between for gender, 88.89, divided by the mean square within. That was 1.83. So notice this 1.83 is used for all three of these F statistics. It's also used for the interaction. So 88.89 divided by 1.83 is 48.49. And the p-value is very, very, very tiny. So this is the kind of difference that is super unlikely to occur if the null hypothesis is true due to random sampling. So we'll reject the null hypothesis there that that men and women have equal alertness, regardless of what kind of drink they had. So next, we'll talk about the within groups, and we'll come back to the interaction in a second. Now for within groups, remember this 1.83, the variance estimate within groups of 1.83, that was just the variance estimate for these 6 cells averaged together. So you calculate the variance of these 3 and do that for all different groups, and you just average those 6 variance estimates. That was this. The degrees of freedom is different than it was previously, right? So this degrees of freedom was 6 minus 1 plus 6 minus 1 plus 6 minus 1. 5 plus 5 is 15. So that's where this 15 came from. This 12 is produced in a very similar way. So now instead of having 3 groups, we have 6. And each group is going to contribute degrees of freedom. So this group of 3 people, their degrees of freedom is 3 minus 1. This is 3 minus 1, 3 minus 1, 3 minus 1, 3 minus 1, 3 minus 1. So each of these groups is contributing 2 degrees of freedom. So there's 1, 2, 3, 4, 5, 6 groups. They each give 2 degrees of freedom. 6 times 2 is 12. So that's where this degrees of freedom came from. And if we wanted to get the sums of squares, we could just multiply this 12 by 1.83, and you get your 22 sums of squares, which of course you could calculate from scratch, but you're not going to be doing that with me. So last, let's talk about this interaction here. So this interaction is not something that I know how to calculate the mean square for. But what I do know is that I can calculate everything up here and everything down here and everything on the bottom. Then what I do is I can take the total and subtract these and these and these, and whatever's left over goes here. And I can do the same for the degrees of freedom. So 17 minus 12, 1 and 2 is going to leave you with 2. Right, and to calculate the mean square, you just divide the sums of squares by the degrees of freedom to get the variance estimate. And then you divide the variance estimate by mean square within, just like you do here. And you get an F statistic that's very small. It's less than 1, so there's no way we're going to be rejecting the null hypothesis, and indeed our p-value is 0.8. That's way bigger than 0.05. So we're going to fail to reject the null hypothesis there. So we don't have evidence that there's an interaction in this case. And then so you can get a better sense of what these results actually look like. I drew the bar graph of these results. So men are the blue bars, women are the green bars, and I put the mean for each of the different groups on top, right? So 4, 5, and 6, this is guys decaf. Their average was 5, so that's where this 5 came from. So there's 3 men in here, and this is their average score. Right, here's the 3 women in the decaf condition. Right? And if you look at this, boy, you can sure tell that women were consistently higher than men. You can also see that overall, these coffee and Mountain Dew drinks had higher alertness than the decaf, although you'd have to do a post hoc test to tell where that difference actually lies. And if we try to draw the lines in to see if they're parallel, I'll do that. And they do look indeed pretty parallel. So the difference here and here is the same, the difference here and here is the same, so there's no interaction. Now, if it would have just looked like this, down here, right here, this is enough for there to have been an interaction, and then our interactions F statistic would have been much larger, potentially even statistically significant, where our p-value is less than 0.01, or our p-value is less than 0.05. And then we'd have rejected the null hypothesis. And notice if there is an interaction, let's say it looks kind of like that, In this case, we could still have a main effect of gender and a main effect of drink, but now there's also an interaction. Let's even make this more extreme. Let's say that women and men are exactly the same down here, right? And so now we have, for uncaffeinated men and women, they don't differ at all on alertness. But now there's a huge boost for women regardless of the source of caffeine, whereas men only get a tiny boost, right? And when there's a significant interaction, people will often say that the main effects aren't really as interpretable as they were if there's no interaction. And that's oftentimes the case. So here, right, for the decaf condition, there really is no main effect. So the main effects are really only occurring across here because of this interaction. And so whenever there is a significant interaction, you really want to try to understand the overall pattern of the results. And oftentimes that's the story, the interpretation that you'll want to take away from your study. We can also compare the effect sizes that we get for the one-way compared to the two-way ANOVA, right? So recall the effect size is eta squared, and that is the sums of squares for a variable divided by the sums of squares total. So for drink here, the sums of squares was 24.78 divided by the sums of squares total, 136.44. So of all the variability, the drink variable explained 0.18, 18%. Now, if we look at drink over here, see the sums of squares between is exactly the same. The sums of squares total is exactly the same. And so regardless of which version of the study you do, or analysis that you do, your eta squared, your effect size for the drink variable is going to be 0.18, so that's not going to change. We can also calculate the effect size, so this would be for drink. We can also calculate it for gender and the interaction. So for gender, the eta squared, we'll say for gender, equals the sums of squares for gender divided by the sums of squares total, and that's 88.89 divided by 136.44, and I divide that, it's 0.65. So gender explained 65% of the overall variability in this whole data set. So that's a huge effect size. Remember the Cohen's guidelines are 0.01 for small, 0.06 for medium, and 0.14 for large, and so a drink here even had a large effect. And then we can do the interaction, so the eta squared, put an x there for the interaction, is the sums of squares for the interaction divided by the sums of squares total. So that's 0.77 divided by the same 136.44. And I calculated that earlier and got 0.01 after rounding up. And so the interaction has a small effect size, although it was non-significant, so we don't want to overinterpret that. Also notice that these effect sizes are, for example, the sums of squares drink divided by the sums of squares total, right? And so the effect size for drink and gender and interaction, when you add all those up, they can't go above 1, right? In fact, if you calculated a effect size for within, with sums of squares within divided by the degrees of freedom total, and you added up the effect size for all four, those would always equal 1. Right? So what we're doing is we're distributing the sums of squares across the variables from this 136. So the maximum sum of all of these effect sizes calculated this way is 1, so that makes it a nice way to get a sense of how much of how the overall variability is distributed, right? And in this data set, it's really distributed primarily by gender, but there is notable variation across the different kinds of drink as well.